Merci beaucoup. Donc, bon après-midi.
Thank you very much and good afternoon, everyone, distinguished guests and participants. First of all, I would like to thank the Science Academy and the Ministry for inviting us in this beautiful place of knowledge. And I would like to thank the and the Prime Minister at the time, Nakasone, for creating this organization that is still as relevant as it was 35 years ago.
And symposium will contribute to our collective efforts to address the pressing climate change challenges and to explore potential solutions. And as someone coming from Canada, where wildfires are raging, I can assure you that climate change means a lot now to many people. As a life scientist myself, and actually a member of the selection committee for the Human Science Frontier Program for many years, I have witnessed the extraordinary projects that were funded over the years, multidisciplinary, international, and that's what we're going to be talking about, how to enable and stimulate further collaborations to address these challenges. Canada was a signatory, a co-founder actually of the Human Science Frontier Program, so it's a great honor for us to continue to support it and to be present here. So for the discussion, I'm going to be joined by esteemed colleagues who will provide us their perspectives on the many areas that perhaps need to be addressed to maintain the momentum, if not accelerate it. And especially in order to accelerate research and discovery in fundamental life sciences and accelerate also its translation into solutions to our pressing challenges. So as we gather here today, you heard that the Human Science Frontier Program was officially born during a G7 summit, and we heard from Minister of Japan a little bit about what happened during the last G7. But allow me to reflect on this recent G7 science meeting as it relates to what we're going to be discussing here today. In addition to the emphasis on researcher mobilities and continued international collaboration, three main issues were discussed at the G7. And you'll see they're interrelated. The first is freedom of research and the promotion of open science. I think we can all agree to that. The second is the importance of research integrity and research security. And I think that's especially important in the context of open science and of collaborations. And of course, these two topics were essential for the thematic, if you want, topics that were raised. So emphasis in terms of international scientific and technological cooperation to solve global challenges such as climate change, but also the use of space, of outer space, and the efforts to further understand and manage our ocean ecosystems. As you can, I think, gather, is quite relevant here. So the new topic on the agenda, the issue of space, as cooperation in the field becomes increasingly vital amid an era of accelerated space exploration. We recognize that space activities are closely linked to finding innovative solutions to mitigate climate change, the destruction of ecosystem, and large-scale natural disasters, whether it's in terms of monitoring, following our progress, and simply readying ourselves to respond to disasters. So I was pleased to sign the statement on behalf of Canada, which also recognized the pivotal role of organizations such as the Human Frontier Science Program. So without further ado, let's get started with our panel today to hear their perspectives about the many challenges and solutions that we need to pay attention to continue the great work that was started over 35 years ago by many member states and an organization that is still present with us, and hopefully for many more years, the Human Science Frontier Program. So to start, I'll invite Marcia McNutt, who's an esteemed scientist and also the president of the US National Academy of Science. And I think, Marcia, it's really befit that you start this, given your own expertise as a sustainability scientist and a geologist. Over to you.
So good afternoon, everyone. Permit me to disrupt this solemn occasion by starting with a joke. So how many academicians does it take to change a light bulb? The answer is change. So after all, the first universities were founded more than 1,000 years ago. And yet, you could take a student from 11th century Bologna and drop them into Stanford University, particularly on commencement day, and they'd feel perfectly at home. They would find students attending classes in stately buildings surrounding a green. They would study in libraries full of ancient lore, and they would see the faculty parading around in gowns, hoods, and caps straight out of the Middle Ages. So despite the relative stability of academia, we are at a time in which change is going to be important, if not essential. Even in the span of my own lifetime, I've seen some powerful forces reshape the academic research enterprise. I'll start with World War II. That helped trigger the global realization that was perhaps best expressed in Vannevar Bush's essay, Science, the Endless Frontier. And he showed that strength in basic research was key to both national security and military might. By the time my own research career began in the 1970s, the level of sponsored research at a given university was used as a proxy for the prestige of that organization. The Bayh-Dole Act, which was passed in the US, bestowed on universities the right to the economic fruits of patented research that came from government funding. That additional resource from patent royalties allowed universities to expand their faculty, attract the best students, obtain the best possible facilities for those faculty, and it increased the division between the have universities, those that were strong in basic research, and those that weren't. The elite universities grew away from those who were not elite. The academic community at that time was still far from diverse. It was mostly white and male. And adding to that lack of inclusivity was the fact that most new understanding was disseminated through journals that were locked behind paywalls. So that fruit of that national investment was not available to everyone. But then came the fall of the Berlin Wall. It fell without a shot being fired. And it came down because the West outcompeted the East in economic opportunity. That triggered the realization that national investment in science was not only for military uses, but one of the most important of the fruits of that national investment was for economic expansion and economic might. These two triggers, the investment by governments and in military, had cascading impacts throughout the academic research environment. For example, federal investment in basic research for economic expansion and the development of the internet, arguably the most disruptive force of the end of the 20th century, gave rise to a new class of megacorporations, such as Microsoft, Google, Apple, and Amazon. The wealth of the founders, in turn, became a runaway economic engine of opportunity as these founders became venture capitalists, and through their venture capital, they seeded money to accelerate the transition from basic research to economically viable products. These wealthy individuals also set up their own personal foundations. And these foundations repaid with interest the national investment in the basic research that led to their success, such that by the year 2015 in the US, research support for basic science, less than half of it came from the federal government. More than half of it came from wealthy foundations and megacorporations. This rise in philanthropic funding resulted in a seismic shift in the culture of academia. Previously, researchers at universities were siloed into science, engineering, social science, humanities, and had little contact with each other. Funding agencies also mirrored this effect in terms of programs that funded science, chemistry, physics, in social sciences and other matters. But then with the rise of these philanthropic organizations, they saw no benefit to this disciplinary structure. They were interested in solving problems, and the problems did not fall neatly into these silos. So philanthropic organizations gave rise to the concept of convergence, which is problem solving by engaging researchers from across the natural, life, engineering, and social sciences to solve the most vexing problems of our time. They funded interdisciplinary centers devoted to topics such as climate change, sustainability, and drug development. And they became the loci for research such that departments mainly focused on education, while these interdisciplinary centers were the hub for research. And some of these philanthropists went even further by building convergence institutes from the ground up. Many were freestanding, and they could break down the disciplinary culture in academia. Good examples were Genelia Farms, that was funded through the Howard Hughes Foundation, the Monterey Bay Aquarium Research Institute, founded by David Packard, and the Harvard-MIT Broad Institute, funded by LA philanthropists Eli and Edith Broad. Which brings me fast forward to today, a time when now equally strong drivers are reshaping the research enterprise for the future. In addition to all of the urgent calls for the community to build viable options to halt climate change, promote sustainability, and reduce inequality, we're at a time when trust in science and scientists is being eroded by mis- and disinformation. AI is inserting itself into many aspects of research, into our scholarship, our communications, and decision-making, at a time when we have scant appreciation for what are not only the promise, but also the perils. These 21st century drivers will prompt even more adjustments to the basic research and higher education enterprise. First, I predict there'll be a new emphasis on something called engaged research, a collaborative approach to inquiry and investigation that connects research with community stakeholders in a partnership of knowledge and action that builds trust and ultimately accelerates benefits to society. Such engaged research is far more likely to result in socially acceptable solutions to major problems like climate change and sustainability than research directions that are pursued without public engagement. Second, educational institutions will need to focus on building human skill sets, unlikely to be done better, faster, and cheaper with AI. Some of those human skill sets are networking, relationship building, creativity, emotional intelligence, and critical thinking skills. I don't know about you, but I will never have a close personal relationship with ChatGPT. Third, we need to revamp science communication. In an age of misinformation, we need to better signal how scientists themselves determine what we trust. We need to build trusted brands and spokespeople for verifying information, and we need to spend more time in two-way dialogue with the public. We have to come out of our scientific silos and build personal rapport with non-scientists. I note in this regard that natural language models, such as used in AI, can be very helpful by transforming even the most jargon-filled science or nature paper into something that an 8th grader can understand. In closing, one thing that is within our purview to change, that most stands in the way of building new bridges, new partnerships, and new opportunities for fundamental science to address the crippling problems of our time. And that one challenge is the current research reward system. Some examples of the misplaced criteria that factor into decisions on hiring, promotion, and tenure include disciplinary-based assessments that discourage young research to venture out of their disciplinary silos and do truly important and interdisciplinary problem solving with people from other fields. Second, emphasis on counting the number of published research papers, the number of citations, H factors, patents, grant revenue, and the impact factor of journals where your work is published. We should instead be considering what is the true measure of societal impact of the work we're doing. And finally, the current reward system has no acknowledgement of the importance of building bridges and trust with the public. In this sense, there's no difference between 11th century Bologna and today. We are still measuring the wrong things for 1,000 years. But I know one thing is true, is that we will be astounded by the pace of change if we simply alter how we are rewarding the scientists and academy people that are important for our future. So thank you very much.
Thank you, Dr. McNutt, for this important perspective and also his historic overview. Coming out of the pandemic, I think your words resonate with many of us, including when it comes to language and communication. So it's now my honor to invite a very eminent scientist. Actually, we are in his court or in his location in many ways, and a personal friend whose groundbreaking work has revolutionized our understanding of immunity. Thank you for that. We needed it the past 3 years more than ever. So without further ado, I'd like to invite Professor Hoffman to come to the floor and share his perspective.
Thank you for those very warm, overblown words. And ladies and gentlemen, distinguished participants, I'm going a step down from the presentation of Professor McNutt, and I'm coming back to basic science, really in the basic sense. And first of all, of course, I wish to express my gratitude to the organizers for the honor of being invited to this high-level summit. I'm particularly elated because one of the organizers, Human Frontiers in Science, was the first international agency to significantly support our research 25 years ago. It was suggested to me that in this short presentation, I describe our studies in Strasbourg on an example of purely basic research. I started my PhD work with Professor Joly, an experimental biologist who had worked on the development of grasshoppers. For this, he relied on transplantations of various organs between individual insects. Although taking no precautions of asepsis in a milieu rich in microbes, he never observed the appearance of an infection. He concluded that these insects had strong antimicrobial defenses and proposed that I study the mechanisms of these largely unknown defenses. I rapidly confirmed the role of blood cells taking up and destroying some of the microbes, but I also noted that this was only one of the facets of the antimicrobial defense. After my thesis defense, I turned with my associates to the fly Drosophila as a model ideally suited for genetic manipulations. Grasshoppers and flies are invertebrates, an animal group representing some 95% of the present-day species, as compared with vertebrates comprising 5% and including humans. Step by step, we were then able to show that the Drosophila immune defense heavily relied on the challenge-induced expression of genes encoding hitherto unknown antimicrobial substances. Peptides, we would say in our jargon. We next asked how flies sense the presence of invading microbes and went on to demonstrate that receptors on the membranes of immune-responsive cells served as sentinels to detect these microbes. Significantly, we could show that this recognition led to the expression of the genes encoding the antimicrobial substances, thus conferring an immune protection to the fly. By that time, similar molecules had been detected in humans, and I established a small international consortium with US and Japanese scientists, and we got the generous support of the Human Frontiers Science Program already mentioned. It rapidly became apparent, thanks to two US groups, one of which was a member of our consortium, that humans produced recognition proteins similar to the immune receptors of the fly. And that, as in the fly, these receptors recognized microbes and activated an immune response. These receptors were called Toll in Drosophila, and their equivalents are referred to as Toll-like receptors in vertebrates, including in humans. In conclusion, these studies had identified in flies the first family of receptors of inborn, we say innate, immunity, and demonstrated that they played a major role in immune defenses, both in invertebrates and vertebrates. Importantly, however, human immune defenses, in addition to the general inborn innate immune response receptors, feature a second, more sophisticated arm termed adaptive immunity with highly variable receptors which are formed on a special blood cell type, the lymphocytes, absent from flies. Over a short period then, it became apparent by independent studies in mice and humans, in the scientific community at large, that these lymphocytes required a signal from the ancient inborn immune system, a signal which is communicated by the toll-like receptors. This signal activates their essential functions, which allow namely for vaccination. And in contrast to earlier assumptions, innate and adaptive immunity, so inborn and adaptive immunity, appear thus to be bridged in vertebrates by this interaction, which is absolutely mandatory for full-blown defense in humans. Following our demonstration of an immune function of toll in the fly, more than 70,000 articles have been published by the scientific community on the immune roles of this family of recognition molecules, particularly in humans. We have learned that they are involved in defense against COVID, that they are detected in tumors and in the brain during neurodegeneration, that they play roles in cardiovascular system, and so on and so on. As I have underlined, we started our studies out of pure curiosity at a time when we had no credible results pointing to perspectives of this type of research. This explains why we had, on several occasions, major difficulties in convincing our university and funding institutions to support our research. Eventually, as the results accumulated over the years, this changed, and in the 90s, we gained support from the European Union, from Japan, from the NIH, and more recently from China. There are many similar examples of blue sky research of this type in life sciences, in chemistry and physics, namely. Of course, I strongly plead that support will always exist to develop this form of bottom-up research. And I have the feeling that is also a feeling which you share with me today, which is not, of course, in any way to disregard the importance of targeted or applied research, which is absolutely vital for society. Funding and organization for effective and sustainable support of basic science have evolved over the years. And I will just mention one very positive evolution in the European Union. That is the creation of the European Research Council, ERC, destined to support cutting-edge and high-risk research, which has the potential to lead to significant breakthroughs and innovations. The ERC bases its decisions for funding solely on scientific excellence. Immediate practical applications of investigator-driven discoveries are not requested. The ERC funding program is universally rated as ideal and is a major flagship within the framework of the much larger Horizon program of the EU. One can only regret that, as so often, the ERC program is limited by the financial constraints and that only a tiny minority, roughly 15% of applicants, can benefit from this support. I would like to add a further regret here concerning the attractiveness of the scientific careers in general. The salaries of our young scientists are not competitive by present-day standards. Keeping in mind that applicants must go through long and competitive years of studies, plus generally periods of postdoctoral work. I urge this summit to plead for more attractive salaries for the young generation of scientists. Further, a major improvement for attractiveness would be to open the recruitment of young scientists to stable positions in significantly larger number than we do now. Let me conclude with the playwright Plautus of ancient Rome 2,200 years ago, sic vertant di, which means, let the gods make this come true. Thank you very much for your attention.
Thank you very much, Professor Hoffman. I think you've illustrated many, very concretely, many important ideas here. One is recruiting and properly funding young researchers. The greatest creativity comes from our younger people. But also, I think the fascinating story of your own research that illustrate the importance of basic research, and many of us are constantly confronted by questions from the public or the politicians about why is it so important to study things like grasshoppers or Drosophila and fruit flies, etc. So I think this is great illustration. So finally, to conclude this, this portion of the panel, I'd like to ask Dr. Nakicenovic, Naki for short, Deputy Chair of the Group of Chief Scientific Advisors to the European Commission, to share his vision with us. And Naki is a very distinguished climate scientist.
Thank you. First, it's an enormous pleasure to be at this important summit and also in this really beautiful historic building. In my opening remarks, I would like to address more general issues, in particular science, sustainable development, and the Earth system. And I will argue, as you will see, that we need a holistic approach, that we can no longer afford to work in silos. All of the systems are related and integrated. And I will illustrate that with a number of slides. So let me start by arguing that the world is at the crossroads. We are facing important challenges on the way forward, multiple crises, polycrises, but if they are resolved in a constructive and positive way, they could lead to achieving safe and just future for all. They could change the historical trends that are going in the wrong direction. And the reason why I'm optimistic is that if you look back at the last 200 years of industrial revolution, humanity has achieved many achievements. For example, economic output has increased 100-fold to about 100 trillion for 8 billion people. So on average, we are relatively well off. Unfortunately, many have been left behind. But if you look at material consumption, such as energy or emissions of carbon dioxide, the factor growth was significantly less. That means that we are becoming ever more efficient, unfortunately not at a high enough rate to offset the growth. And so that has led to many planetary challenges. The global mean temperature has increased by well over 1 degree. But I would also like to mention that regional and indoor air pollution leads every year to about 8 million premature deaths. These are some of the really huge challenges on the way forward. And to make a problem even bigger, I think we are on the verge in coming decades on transgressing planetary boundaries, even though many people, billions, are left behind without access to energy, water, or sanitation. So what I would like to argue is that the 2030 agenda with the 17 SDGs and the Paris Agreement are a huge gift to humanity. Hopefully, they will change the direction of development, both for the people and the benefit for the planet as well. So let me go to something that I think you're all familiar with, which is the temperature increase of the Earth since 1880. And in particular, if you look at the last half a century, really accelerated increase in the temperature indicated by the red curve. But the science was clear half a century ago. And in 1988, IPCC was created for that reason, to provide even more robust science. Then we had Kyoto Protocol in '97 and significantly Paris Agreement for 2015. So you might ask the question, why did climate system not notice all of these efforts that we are making? Well, the answer, I'm afraid, is relatively simple, because the emissions are continuing to increase after a very brief lull during the COVID pandemic. We are back on the historic trend, as you can see. And that, in the long run, if we don't change the way the humanity is developing, will lead to multiple problems. I would like to show you recent results of the Earth Commission, just published in Nature. I'm showing you here 9 tipping elements in the Earth system. By tipping, what one means is that the critical function of a system would be irreversibly changed to a new state. And in this case, it might mean that the erosion of the life support systems on the planet. And as you can see, all 9 are really related. Perhaps the labels are too small to see. Let me just mention a few examples. Permafrost in the north, Brazilian rainforest, and then in the south, West Antarctic ice sheet. All of them are threatened, and on top of it, they're related and clearly related to our activities. On the right, you see the coral reefs that are already threatened today. And one of the conclusions of the Earth Commission is that at 1.5 degrees, we would have a likely tipping of 4 of the Earth systems, and at 2 degrees, already 6 systems. So I think these are some of the reasons to worry, and the question is, what can we do about it? But I think we all know it. We need to reduce the emissions. I call that the carbon law. This is based on a publication in Science we made 6 years ago, and has been in the meantime confirmed by IPCC and many other scientific publications. If you look at this graph on the vertical scale, you see global emissions of carbon dioxide. We are emitting 40 billion tons every year, and increasing into the future. And what we need to do is exactly the opposite. And that's why I call it carbon law. We need to reduce the emissions by half every decade to reach net zero by the middle of the century. And this will require a fundamental transformation of most of our activities, our lifestyles, shifting to carbon-free electricity and many other services. But this will unfortunately not be enough. In the yellow and orange, you see the need to remove the carbon from the atmosphere, because we are so late in reducing the emissions. Hopefully this will be the nature-based solution. So I've put an icon of the European Bauhaus. The idea there is to sequester carbon into wood and other building materials, create very pleasant and hopefully beautiful urban environment for the people. That's also anchored in the European Fit for 55 legislature. Half emissions this decade, go to Europe being first carbon-free continent by the middle of the century. But we might need also carbon capture and storage on the way forward. And you can see the scientific opinion of the group of chief scientific advisors to the European Commission. During the last decade, we have published 16 scientific opinions on the way forward, on the policy. This is on energy. Others have ranged from issues of carbon capture and storage to cancer monitoring and so on. But the last thing I wanted to mention is blue and green curve. This is the gift of the Mother Nature to us. It removes right now about half of our emissions from the atmosphere, and that's likely to weaken as the planet warms. So these are the challenges on the way forward. Now, these have been known, as I said, for decades in the science. And a few years ago, we have initiated an activity called The World in 2050, where we have tried to provide science base for the 2030 agenda with its 17 Sustainable Development Goals and 169 targets. And the reason of going in that direction is this is exceedingly complex if you really think about it. Very few people really understand on the way forward. It's not that actionable. Perhaps that explains why we are so far behind. And so what we have developed are the 6 transformations that, if they were achieved, we would be on the best way of a sustainable development for all. I would also like to highlight that very similar 6 transformations were proposed in the Global Sustainability Report in the UN, and would like to recognize also International Science Council representing the scientific and engineering community in these processes. So there are many processes going on, but I think it is important to simplify the agenda in order to make it operational. And I would like to say a few words about the digital revolution. All of these things are related to each other, but I think digital challenges are ahead of us, both in terms of a threat and an opportunity. And I would like to illustrate the power of digital revolution here to you based on these icons. And I'm sure you cannot read them. Let me just say the blue ones refer to change in our lifestyles from ownership to usership. The middle ones are about sharing economy and recycling. And importantly, the yellow ones are about the systemic change. All of those things can be catalyzed with the digital revolution if it's steered in the right direction, because these are what we call granular technologies, technologies that can diffuse very, very quickly. So let me conclude here by just making a couple of final observations. We need to change our lifestyles and preferences. This is not just a technological fix. This is why it's so difficult. The next generation, I think, is already doing that, going to services rather than ownership. We need new business models and behaviors to achieve the shared and circular economy. And the digital revolution, as I mentioned, is perhaps the way forward. Just let me give you one example. I would fully agree that ChatGPT should not be our friend. It can be even dangerous, but it can be very useful. And let me just mention that it started 7 months ago, and today there are 2 billion users in the world. The diffusion speed is incredible. So we need very serious social steering on the way to sustainable future for all. Thank you very much. These are the two publications on which I base some of my comments.
Thank you, Dr. Naki, for this quite compelling, actually, expose. Now, I think we need to gather all the science that we need, whether it's for behavioral change or technological advances. And on this, I will go down to join my other panelist members we have, I think, time for a couple of questions. Thank you. Yeah, okay. So now we're doing a roundtable from here. I hope everyone can see us. I'm just going to dig a little bit on some of the issues that were raised by the panelists. And Dr. McNutt, I'd like to start with you. You talked about change and our need actually to change how we're organizing our institutions, how we're evaluating researchers. Can you just expand a little bit on this to try and see practically, how can we go about this renewed evaluation concept?
Yes, thank you very much for that question. So I think we have some examples out there of institutions that are already doing that. Just to give you one case in point, when I was director of the U.S. Geological Survey, we had an appointment that was sort of a super grade that scientists could aspire to, that was above the usual government rankings. And it was reserved for scientists who made unusual and compelling contributions, but weren't in management. And I remember when one young man came up for that promotion, he was the youngest who had ever been considered. And when we got letters on him, we didn't go for letters to academics. We went for letters from the Red Cross, from the Premier of China, and they talked about his contributions in terms of lives saved. And he had developed a new method for processing scientific data, seismic data, that took all the latency out of the system so that as soon as an earthquake occurred, within 2 minutes, the USGS could get a report to the relevant group, whether it was a local event, a regional event, a national event, or an international event, that showed who had to mobilize to protect people. And so I think lives saved is a perfect, reasonable way to judge academicians, or jobs created, or other things.
So essentially impact, whether it's societal impact, community impact, scientific impact, I think it's more broadly. I think that many young people actually relate to this. I see the students in our labs and classrooms. I think they understand this. Jules, you talked about being funded as a young researcher with your colleagues from Japan and the US. So these days, our students in our labs, they see us stressed out, having to fill out a lot of grants and papers, and we seem to be discouraging them. I don't know if you have a perspective on how we can do better to support the young researchers or the early career researcher.
It's a very old question. And the whole community has been confronted with that. So it's a question, what is this young lady, this young man worth for science? Is he really good? On what will you base it? Well, classically it was your curriculum during the studies, but that does not go very far. And so then there were two attitudes. There was the future supervisor who would say, well, this person is fine, I like him and I get along well with him, and he would hire him. But that's gone now, because hiring is committees. Those are committees, and committees will not agree on that sort of thing. And then we came to a situation now where you have many, many applicants. For instance, and I'm not going to speak too much about the French system, but many applicants for one position, and it's very delicate to decide. And we make many mistakes also. For instance, one of the classical mistakes here was to hire one who had been for 3 or 4 years as a postdoc in the United States and had one first author paper in science, and he came over and then it was finished. So that's, I have no, surely I have no personal position there. I just, it's sort of a gut feeling of the supervisors, and talk with the person, see the person work for a short period and so on. And so this man is, he will do it.
But you also, you know, sort of advocated for more permanent positions and
yes, yes,
and
I mean,
better
yes,
funding.
Of course. More permanent position, that's obvious. I mean, when I was, I used to chair those recruitment panels, and at that time in my subfield, there would be per year in major funding agency here about 15 permanent positions. Now we are down to not 1/3 of that. And we have an increasing number of young people, of course, because we form a lot of young people, and among them they're very good people. So it's sort of a dead end in our system. And I'm speaking not of the French system, the same problem in Germany and in the UK. And it's worse even in China, because they form so many young people and they don't have that many positions.
Well, we need a lot of innovation to address climate change. So I hope that governments, institutions, and the private sector can work together to stimulate more research and find more positions for these young people. Maybe the last question for you, Dr. Naki. We talked about ChatGPT. You mentioned digital. I can't help but think about AI like we thought about genomics when the Human Science Frontier Program was actually first set up. So there were ethical issues, there were, you know, all sorts of questions. How do you see the intersection of AI, digital data with the life sciences and the sustainable solutions that we need to develop?
Thank you. That's a very tough question. I'll do my best to try to respond to it. But if I may, let me just comment on what you said before and what Marcia said. You know, I think there is a great danger for science in the long run. We have enormous challenges, yet we work in disciplines, and I think quantitative indicators, even if we all think they're insufficient, at the end might win when there are lots of applicants for a position. So science needs to be funded sustainably to answer also the questions I think that you have posed. So the digital revolution is basically creation of science, if you wish, and research and engineering, and the convergence of digital technologies. And it's a huge huge set. It's artificial intelligence, robotics, additive manufacturing, and so on. The convergence of these technologies might be exceedingly powerful. And the reason why I'm saying that is we have strong historical analogs. If you look at the digital telephone, the mobile telephone, it was introduced 30 years ago, and everybody in the world, both in the global south and global north, has a phone, and we can hardly live without it. It has changed our lives. So the question is how the digital revolution in the next wave, that might also last 20, 30 years, perhaps might be even faster, if ChatGPT is an example, how are we going to socially steer that? Because there are clearly many dangers. One of the questions we asked in the world in 2050 is what would be the role of human beings, not just research, in a world dominated by artificial, self-organizing, clustering devices? So I think this is a key question, and this is why I think we need the integrative approaches. We cannot work in silos, what you mentioned. We need a holistic approach and what I call social steering, for the lack of a better word. I think we need regulation, but I think we all have to participate in it. This needs to be an inclusive process that we can steer the process in the right direction.
I couldn't agree more, and I think these are great words to conclude our panel that is setting the stage. In the coming days, we're going to explore all these topics deeper and hopefully come up with some recommendations and solutions. But I think that the challenges facing us demonstrate how relevant organizations like the Human Science Frontier Program are and how important it is to maintain investments in basic science. So on this, thank you to our panelists and to our audience.